Every once in a while, astronomy reveals something that feels less like nature and more like physics pushed to its absolute limit, showing us what matter can do under conditions we can barely imagine. There are remnants of dead stars out there, spinning not once a day like our Earth, but hundreds of times every single second, without ever stopping. The fastest one we have found rotates 716 times in the span of a single second, a number that takes a moment to truly absorb. This is a real thing, spinning right now, somewhere in the darkness of our galaxy, as these words reach your ears tonight. Encountering this kind of speed for the first time brings a quiet sense of surprise, a recalibration of what the universe seems to allow. 716 rotations per second means each full spin takes less than 1.5 thousandths of a second to complete from start to finish. In the time a hummingbird beats its wings just once, this object has already completed more than 10 complete revolutions around its own axis. The spin is so fast that ordinary intuition struggles to picture it properly, requiring us to think in different terms than everyday experience provides. You're listening to The Drowsy Astronaut, where we explore the cosmos in a slow and unhurried way that allows rest to arrive naturally on its own. Tonight we are spending time with pulsars, these spinning remnants of ancient stars, following wherever the science leads us without any rush or pressure to hurry along. If you are joining for the first time, feel welcome to share where you are listening from in the comments whenever you have a moment to spare. And if you enjoy these slow explorations, a like or subscribe helps others find their way here too. But for now, let us settle in with the remarkable speed of these spinning objects. To understand what 716 rotations per second actually means, it helps to find comparisons that bring the number down to something we can hold in our minds. A figure skater performing a very fast spin might complete about 5 rotations per second at their absolute fastest, with arms pulled in tight against their body. A household ceiling fan might spin at perhaps 50 rotations per second on its highest setting, creating that familiar blur where individual blades become invisible to the watching eye. The fastest pulsar spins more than 14 times faster than even that fan, completing each full rotation before the fan blade has moved even a small fraction of the way around. The surface of this fastest pulsar moves at a speed that approaches a significant fraction of the fastest thing in the universe, light itself. Light travels at about 300,000 kilometers every second, the fastest anything can move according to our current understanding of physics and the nature of space. The equator of this spinning pulsar moves at roughly 70,000 kilometers per second, racing around the axis at nearly 1/4 of that ultimate cosmic speed limit. Material at the surface moves faster than any spacecraft humanity has ever built, faster than any bullet, faster than almost anything we have ever measured. This extraordinary speed raises a natural question that feels important to consider. How can something spin this fast without simply tearing itself apart from the forces involved? When any object spins, the material on the outside experiences an outward pull, wanting to fly away from the center of rotation due to the circular motion itself. A washing machine on its high spin cycle exerts noticeable outward force on the clothes inside, and that machine spins perhaps 30 times per second at the very most. The fastest pulsar spins more than 20 times faster than that washing machine, yet it holds together completely, remaining intact despite forces that would shred ordinary objects instantly. The answer to this puzzle lies in what the pulsar is actually made of, something we will explore more deeply as our journey continues through the coming hours tonight. For the moment, the essential fact is that the gravity holding this object together is extraordinarily strong enough to overcome the tremendous outward pull of such rapid rotation. The material is packed so tightly, and the gravitational pull inward is so intense that even spinning at these incredible rates cannot break the object apart into pieces. Gravity wins this contest between flying apart and holding together, but only because the gravity here is unlike anything we experience on Earth or anywhere nearby. What makes the spin of pulsars particularly remarkable is not just the raw speed, but also the steadiness with which that speed is maintained over immense stretches of time. This is not chaotic spinning or a wobbling tumble through space, but a precise and regular rotation that repeats with extraordinary consistency, day after day, year after year. Each rotation takes almost exactly the same amount of time as the one before it, with variations so tiny that only the most sensitive instruments can detect them at all. The regularity is so precise that pulsars serve as some of the most accurate natural clocks in the entire universe, more stable than anything humans have ever built. The spin of the fastest pulsar has been measured with remarkable precision, holding steady at 716.05 rotations every single second, without significant variation. That tiny decimal, the 0.05, demonstrates just how precisely astronomers can measure this spinning object that lies thousands of light years away from Earth and our instruments. From such a vast distance, detecting the spin rate down to 1/100th of a rotation per second speaks to the remarkable precision that modern astronomy has achieved. The pulsar does not know or care that we are watching, but the steadiness of its spin allows us to measure it with this extraordinary level of accuracy. Each complete rotation of the fastest pulsar takes about 1.4 milliseconds, which means 1.4 thousandths of a second from the start of one spin to the start of the next. A millisecond is a very short span of time, short enough that human senses cannot perceive individual events happening on that timescale with any real clarity or distinction. The blink of a human eye takes roughly 300 to 400 milliseconds to complete, so several hundred pulsar rotations happen during a single casual blink of your eyes. By the time your eyelids close and open again in the most ordinary of blinks, this pulsar has already spun around more than 250 complete times. The speed can also be understood in terms of frequency, which is how scientists typically describe and communicate pulsar rotation rates in their measurements and research papers. A frequency of 716 Hz means 716 complete cycles happening every second, similar to how we describe the pitch of musical notes and sounds. If you could somehow hear this rotation as an audible sound, it would be a fairly high note, higher than most everyday sounds, but still within the range of human hearing. Some pulsars spin slowly enough that their rotation would sound like a low drum beat, while this fastest one would produce a high and steady tone. The stability of the spin becomes even more striking when considering how long these objects have been rotating without any significant change to their fundamental rhythm. Pulsars have been spinning for millions of years in many cases, maintaining their rotation through all that vast time with only the most gradual slowing over the ages. The fastest pulsars, often called millisecond pulsars because their periods are measured in those tiny fractions of a second, actually slow down even more gradually than their slower cousins elsewhere. Some of these fast spinners will continue rotating at nearly their current speed for billions of years still to come, slowly running down but never stopping abruptly. The energy contained in this spinning motion is enormous, even though the object itself is quite small compared to the ordinary stars we see in the night sky above. Rotational energy depends on how fast something spins, and also on how much mass is involved in that spinning motion around the central axis of rotation. A pulsar typically contains about 1.5 times the mass of our entire sun, all of that matter packed into a space only about 20 kilometers across in total diameter. All that mass spinning hundreds of times per second contains enough rotational energy to power all of human civilization for billions of years if we could somehow capture and harness it. The fastest known pulsar carries a catalog name that serves more as a set of coordinates than a proper name in any traditional or personal sense of the word. Scientists refer to it as PSRJ 1748 minus 246 AD, a string of letters and numbers that tells astronomers exactly where in the sky to point their instruments. The name might seem cold and technical, but it points to a real object spinning in a real place, a specific location within our own Milky Way galaxy. This particular pulsar lives within a dense globular cluster where many stars crowd together, which is part of why it spins so remarkably fast in the first place. The extraordinary spin of this pulsar did not come from its original formation, but developed later through a process that astronomers call recycling, something we will explore in greater depth as our journey continues. For the moment, it is enough to know that the speed we observe today represents the end result of a long history stretching back millions upon millions of years. The pulsar was not always spinning this fast, and the story of how it reached this remarkable rate involves other stars and dramatic transfers of material between them. That story will unfold as we continue, but the speed itself remains the central wonder that defines the fastest pulsar among all those we have discovered. Across our galaxy, astronomers have found about 3,000 pulsars so far, each one spinning at its own characteristic rate that distinguishes it from all the others. Some spin slowly, taking several seconds to complete a single rotation, their activity proceeding at a leisurely rhythm that feels almost stately and calm by comparison. Others spin faster, completing many rotations per second, their signals flickering rapidly as they sweep past our detectors here on Earth, thousands of light years away from their locations. The distribution of spin rates among known pulsars tells us about how these objects form and how they change over the long ages of their existence. In the quiet darkness, the slowest pulsars might rotate once every few seconds, a pace that seems almost lazy compared to their faster cousins spinning elsewhere throughout the scattered populations of the galaxy. These slow spinners are often older objects, having already lost much of their original rotational energy through a gradual process of slowing down over millions and millions of years. The fastest pulsars, like our 716 Hz example, represent a special category that somehow acquired or maintained extraordinary spin rates against the usual pattern of gradual decline. Between the slowest and fastest lies a whole population of pulsars spinning at various intermediate rates, each one a unique individual with its own particular history. What all pulsars share, regardless of their spin rate, is the fundamental nature of what they are, the collapsed cores of stars that once shone with ordinary light, like our sun does today. A pulsar is essentially a dead star, or more precisely, the extremely dense remnant left behind after a massive star exhausted all of its fuel and collapsed dramatically inward under its own gravity. This collapse compressed the core to extraordinary density, and the spin we observe today traces back to that collapse and to the physics of how rotating objects behave when they shrink dramatically in size. The faster the original star was spinning before its collapse, and the more dramatically it shrank, the faster the resulting pulsar would spin once the collapse was complete and finished. The relationship between size and spin follows a principle that ice skaters demonstrate beautifully when they pull their arms in during a spin to rotate faster and faster. When a spinning object becomes smaller while keeping its rotational momentum, the rotation rate must increase to compensate for the reduced size of the spinning mass and its distribution. A star that once spun slowly over the course of weeks or even months becomes a pulsar, spinning many times per second after the dramatic shrinking of the collapse occurs. This simple principle explains the basic origin of fast pulsar spin, though the very fastest pulsars have additional stories involving companion stars and transfer of material between bodies. Sitting with the idea of 716 rotations per second allows a kind of quiet appreciation to develop for what the universe makes possible within its physical laws. Objects on Earth simply cannot spin this fast because the forces involved would tear them apart long before they reached anything close to these rotation rates. Only something held together by incredibly strong gravity can withstand the outward pull that such rapid rotation creates at every point along the spinning surface of the object. The pulsar exists in a realm of physics where conditions differ so dramatically from our everyday experience that the normal expectations seem to bend and flex into new shapes. The spin is the defining characteristic that makes pulsars observable across the vast distances that separate them from Earth and the instruments we use to detect their signals. Without the spin, there would be no pulse, no regular signal reaching us from the darkness of space, nothing to alert us to the presence of these objects hiding among the stars. The dead star would simply drift invisibly through space, too dim to see by its own faint glow, lost among the countless other dim objects scattered everywhere throughout the galaxy. But because it spins, and because that spin creates a sweeping beam of radiation, the pulsar announces its presence across light years of emptiness with each rotation. That beam, sweeping through space with every rotation, reaches Earth as a regular pulse of radio waves arriving from a specific point in the distant sky above our instruments. The pulse comes once per rotation, so a pulsar spinning 716 times per second sends 716 pulses every second toward any observer positioned along the path of its sweeping beam. Each pulse represents one complete revolution of the object, one full trip around the axis, one sweep of the beam past our particular line of sight to that distant location. The regularity of those arriving pulses matches the regularity of the spin itself, and both remain extraordinarily stable over timescales that dwarf all of human experience and recorded history. The speed of the spin has been our home base throughout this first portion of our journey, and it remains a subject worthy of extended appreciation and contemplation. 716 rotations per second, each one taking just over a millisecond to complete, the surface racing at nearly a quarter of the speed of light itself. Endlessly. The spin has continued for ages already, and will continue for ages more, steady and regular, a cosmic rhythm keeping time somewhere in the darkness between the stars of our galaxy. And with each rotation, a beam of radiation sweeps through space, reaching across the light years, touching distant worlds including our own. And that sweeping beam is where our attention turns next. The spinning of a pulsar creates something remarkable that reaches far beyond the object itself, a beam of radiation that sweeps through the surrounding darkness of interstellar space. This beam is what makes pulsars detectable to us, across the tremendous distances that separate these objects from Earth and our watching instruments below on the surface. Without the beam, the pulsar would be just another dark and invisible remnant drifting silently through the galaxy, unknown and undetectable by any means we currently possess. With the beam, the pulsar becomes a cosmic lighthouse, sending a signal across light years to announce its presence to anyone or anything capable of receiving it. The lighthouse comparison helps make the behavior understandable in terms of something familiar from ordinary experience here on Earth and along our coastlines. A traditional lighthouse sends out a beam of light that rotates as the mechanism inside turns, sweeping that beam across the water in a regular pattern that repeating ships can recognize. A sailor watching from a distance sees not a constant light, but a regular flash each time the rotating beam sweeps past their particular line of sight toward the lighthouse. The interval between flashes tells the sailor which lighthouse they are seeing, since each one has its own characteristic timing and pattern that identifies it uniquely. Pulsars work in almost exactly the same way, with the spinning of the object causing the beam to sweep through space in a circle, with each complete rotation around the axis. An observer positioned along the path of that sweeping beam sees a flash or pulse each time the beam passes their location, then darkness until the beam comes around again. The interval between pulses corresponds exactly to the rotation period of the pulsar. So a pulsar spinning 716 times per second produces 716 pulses every single second. The regularity of these pulses, their precise timing and consistent strength, is what first caught the attention of astronomers when pulsars were initially discovered decades ago. The beam itself consists of radiation, which is a form of energy that travels through space at the speed of light, in the form of waves or particles, depending on how you choose to describe it. Most pulsars emit their beams primarily at radio wavelengths, which is a form of light that human eyes cannot see, but that radio telescopes can detect very effectively. Some pulsars also emit beams at higher energies, including visible light, X-rays, and even gamma rays, though these are less common and require different instruments to observe and study. The fastest pulsar we have been discussing emits its beam at radio wavelengths, which is how astronomers detected it and measured its remarkable spin rate. The beam streams outward from near the magnetic poles of the pulsar, which are usually not aligned with the axis around which the object actually spins and rotates. This misalignment between the magnetic poles and the rotation axis is crucial for creating the lighthouse effect that makes the pulsar detectable from afar. If the magnetic poles were aligned perfectly with the rotation axis, The beam would always point in the same direction and would either always hit Earth or never hit Earth at all. The tilt between these two axes means that the beam sweeps around in a cone as the pulsar rotates, sometimes pointing toward Earth and sometimes pointing away into other regions of space. The beam travels through space at the speed of light, covering about 300,000 kilometers every second as it journeys outward from the pulsar toward wherever it happens to be pointed at any given moment. This means that the pulses we detect on Earth left the pulsar some time ago, with the travel time depending on the distance between us and that particular spinning object. A pulsar located 1,000 light-years away sends pulses that take 1,000 years to reach us, meaning we see the pulsar as it was a millennium ago rather than as it is right now. The fastest pulsar lies deep within our galaxy, and its pulses have been traveling for thousands of years before finally arriving at our radio telescopes. The journey of each pulse through interstellar space is not entirely unemphatic, as the thin material scattered between the stars affects how the pulse arrives at Earth and our waiting instruments. Space is not truly empty, but contains a sparse scattering of particles, mostly hydrogen atoms and free electrons, drifting through the vast reaches between stellar systems. These particles interact with the radio waves of the pulsar beam, slightly slowing them down and spreading them out as they travel through the intervening medium toward our position. The effect is small but measurable, and astronomers use it to learn about the material distributed through space between us and the pulsars we observe. When the beam finally reaches Earth, after its long journey, it arrives as a brief pulse of radio waves, lasting only a fraction of a second before fading until the next rotation brings the beam back around. Radio telescopes detect these pulses as small increases in the radio signal coming from the direction of the pulsar, blips of energy standing out against the background noise of the radio sky. The precision of modern instruments allows astronomers to time the arrival of each pulse with extraordinary accuracy, measuring exactly when each one reaches the telescope down to tiny fractions of a second. This timing precision is what reveals the rotation rate of the pulsar so exactly, with each pulse marking one complete spin of the distant object. The pulses arrive with remarkable regularity, tick after tick after tick, like the ticking of a cosmic clock that has been keeping time for millions of years without variation. The best pulsar timers maintain their rhythm so precisely that they rival or even exceed the accuracy of the atomic clocks that humans have built here on Earth. This regularity made the discovery of pulsars initially confusing because natural objects were not expected to produce such perfectly regular signals without any variation or drift over time. For a brief period after the first pulsar was discovered, some scientists wondered whether the signal might be artificial, a beacon created by an intelligent civilization somewhere in the galaxy, reaching out. The beam does not reach every part of the galaxy equally, since it streams outward in a relatively narrow cone that covers only a small fraction of the sky around the pulsar. Most of space never sees the beam at all, as it sweeps past in a circle that covers only certain directions with each rotation of the spinning object. This means that we can only detect pulsars whose beams happen to sweep across Earth, missing all the ones whose beams point in other directions throughout the entire sky. Astronomers estimate that for every pulsar we detect, there may be 10 or more pointing in directions that never intersect with our line of sight from this particular corner of the galaxy. The geometry of the beam affects what we observe in ways that help astronomers understand the structure and physics of these remarkable objects. Some pulsars show a single pulse per rotation, meaning their beam crosses Earth once during each spin around the axis of the object. Others show 2 pulses per rotation, if both magnetic poles produce beams that happen to sweep across our position during each complete cycle of rotation. The width of the pulse, how long it lasts during each rotation, tells us about the angular size of the beam cone and how it is shaped near the pulsar itself. The beam carries information about the pulsar itself, encoded in its properties, in ways that patient analysis can extract and interpret into understanding. The polarization of the radio waves, meaning the orientation of the electromagnetic vibrations, reveals details about the magnetic field near the pulsar, where the beam originates and is shaped. The spectrum of the radio waves, meaning which frequencies are stronger or weaker, tells us about the processes that created the beam in the first place and continue to sustain it. Each pulse is a tiny package of data sent across the light years, containing clues about conditions at the surface of a dead star spinning in the distant darkness. The brightness of pulsar beams varies enormously from one object to another, with some producing relatively faint signals and others broadcasting quite powerfully into space. The brightest pulsars can be detected from enormous distances, their beams strong enough to remain visible even after traveling thousands or tens of thousands of light years through the galaxy. Fainter pulsars can only be seen if they are relatively close, within a few hundred light years or so, limiting our ability to detect them to our immediate galactic neighborhood. The fastest spinning pulsar produces a moderately strong beam, bright enough to detect from its location deep within a dense star cluster far across the galaxy from our position. The beam persists for as long as the pulsar continues spinning and continues to have the conditions necessary to generate the radiation in the first place. Young pulsars, newly formed from stellar collapse, typically produce strong beams that are easily detected across great distances by our radio telescopes and instruments. As pulsars age and slow down over millions of years, their beams gradually weaken until eventually they fade below the threshold where we can detect them at all. The pulsar does not stop existing when this happens, but it stops being visible to us, becoming just another dark neutron star drifting invisibly through the galaxy. The energy that powers the beam comes ultimately from the rotational energy of the spinning pulsar, which gradually decreases as the beam carries energy away into space over time. Each pulse that streams outward into the darkness represents a tiny amount of rotational energy converted into radiation and sent away from the pulsar forever. Over time, this energy loss causes the pulsar to spin slightly more slowly, with the rotation period gradually increasing by tiny fractions of a second as the ages pass. The process is extremely gradual for most pulsars, taking millions of years for any significant slowing to occur. But it is continuous and inevitable for all of them. The beam that we detect on Earth represents only one sliver of the radiation that the pulsar produces during each rotation around its spinning axis. The cone of the beam might be a few degrees wide, meaning it covers only a small fraction of the sphere surrounding the pulsar in every direction outward. Most of the beam's energy streams off in directions that miss Earth entirely, illuminating regions of space that no one is currently watching or that contain nothing to receive the signal. We happen to be positioned along one particular line of sight through the beam cone, which is the only reason we know this particular pulsar exists at all. The thought of this beam sweeping through space continuously, rotation after rotation, century after century, creates a picture of patient persistence across timescales that dwarf human experience entirely. The pulsar we observe tonight has been sending its beam through space since long before any human looked up at the stars with wondering eyes or questioning minds. The beam will continue sweeping through space long after everyone currently living has passed, long after our civilization has transformed into whatever comes next, long after the Earth itself has changed beyond recognition. The beam simply continues, one rotation after another, pulse after pulse, crossing the darkness between the stars without pause or purpose beyond its own existence. Somewhere in our galaxy right now, countless pulsar beams are sweeping through space, most of them invisible to us because they point in directions we cannot see from our particular vantage point. The 3,000 or so pulsars we have detected represent only a small fraction of the total population that must exist, with estimates suggesting perhaps 100 million neutron stars scattered throughout the Milky Way galaxy. Most of these produce no beam at all anymore, having slowed down beyond the threshold where the lighthouse mechanism operates, drifting silently through the darkness as invisible relics of ancient stellar deaths. But many still spin, still beam, still send their signals outward into space, even though no one may be positioned to receive them from that particular angle. The beam connects us to the pulsar across the intervening light years, a thread of radiation spanning the enormous distance that separates our small world from that rapidly spinning remnant. Without this beam, we would never know the pulsar existed at all, never measure its spin rate, never wonder at its properties, or ponder what it means. The beam is both the messenger and the message, carrying information about its source, while also simply being the phenomenon that makes the source visible and knowable from afar. When we observe a pulsar, we observe its beam, and through that beam we learn about the strange and dense object that creates it with each rapid rotation. The source of this beam, the object that spins and creates the sweeping lighthouse effect we detect from Earth, is unlike anything else in the known universe, except for other objects of its same exotic type. It is a star, but not a star like our sun, or like any of the familiar stars visible on a clear night sky above us. Looking upward, it is the collapsed remnant of a star, compressed to a density so extreme that the matter inside has been crushed into forms that do not exist anywhere else in the cosmos we have explored. Understanding this object, this neutron star that spins so rapidly and beams so persistently, is where our journey takes us next as we continue deeper into the night. The object that spins and sends its beam across the galaxy is something that challenges ordinary understanding of what matter can become under extreme conditions and pressures. This is a neutron star, the collapsed core of what was once a much larger star that exhausted its fuel and underwent a violent transformation long ago in the distant past. What remains is a sphere of matter compressed to densities that exist nowhere else in the observable universe except inside these particular objects, and perhaps within black holes themselves. The entire mass of a star like our Sun, or even more, has been squeezed into a ball roughly 20 kilometers across, about the size of a moderately large city on Earth. 20 kilometers seems impossibly small to contain the mass of an entire star. Yet, this is precisely what a neutron star achieves through the power of gravitational compression during stellar collapse. For comparison, Our Sun is about 1.4 million kilometers in diameter, roughly 70,000 times larger than a typical neutron star in linear measurement terms. All of that solar mass, compressed down to 20 kilometers, creates a density so extreme that ordinary language struggles to convey its true magnitude and implications. A single teaspoon of neutron star material, if somehow transported to Earth, would weigh roughly 1 billion metric tons, more than every car and truck ever manufactured, combined in a spoonful. This extraordinary density arises from the complete crushing of normal atomic structure that occurs during the formation of the neutron star under its own gravity. In ordinary matter, atoms consist mostly of empty space, with a tiny nucleus at the center and electrons orbiting at relatively vast distances from that central core. The nucleus itself contains protons and neutrons, and the space between the nucleus and the orbiting electrons gives matter its normal size and density that we experience every day. In a neutron star, all of that empty space has been eliminated, with electrons forced into the protons to create neutrons, leaving behind a material made almost entirely of neutrons, packed together as tightly as physics allows. The name neutron star comes directly from this composition, a star made primarily of neutrons, rather than the normal atoms that make up ordinary matter, including our own bodies and the Earth beneath us. Neutrons are particles that normally exist inside atomic nuclei, contributing to the mass of atoms, but carrying no electrical charge, unlike the positively charged protons or negatively charged electrons. When pressed together under extreme conditions, neutrons can pack much more tightly than normal atoms because there are no electron shells to take up space and keep particles separated. The result is a material with a density roughly equivalent to packing the entire human population of Earth into a space the size of a sugar cube. The gravity at the surface of a neutron star reflects this extreme density, creating conditions that would be immediately fatal to any material object from everyday experience approaching or touching the surface. The surface gravity is roughly 200 billion times stronger than the gravity we experience on Earth, a number so large it becomes almost meaningless to human intuition and understanding. An object dropped from a height of 1 meter above the surface would hit the ground at about 7 million kilometers per hour, fast enough to vaporize on impact instantly and completely. Nothing from our everyday experience could survive even briefly in such an environment, where gravity dominates everything that happens at every scale. The escape velocity from the surface, meaning the speed needed to leave the neutron star and never fall back, is about 1/3 the speed of light itself. This is remarkably close to the ultimate speed limit that physics imposes on all movement through space, showing just how intense the gravitational field has become around this compressed object. Light itself, when leaving the surface, must climb out of this deep gravitational well and loses some of its energy in the process, becoming slightly redder as it escapes. The neutron star approaches, but does not quite reach the threshold that would turn it into a black hole, from which not even light could escape at all. The interior structure of a neutron star remains somewhat mysterious, since we cannot directly observe what lies beneath the surface of these distant and exotic objects hidden in the depths of space. The outer crust likely consists of a crystalline lattice of iron nuclei, arranged in a regular pattern like the atoms in a metal, but under conditions of extreme pressure and density. Beneath this crust lies a fluid of neutrons, flowing like a superfluid with no friction or resistance, possibly permeated by currents of superconducting protons carrying electrical charge without any resistance at all. The very core may contain even more exotic forms of matter that do not exist anywhere else in the universe, and that we do not yet fully understand or have names for. The surface of a neutron star is smoother than anything on Earth, with the maximum height of any mountain or bump limited to about a centimeter or less by the crushing gravity. On Earth, mountains rise kilometers into the sky because our planet's gravity is weak enough to allow rock to pile up without collapsing under its own weight entirely. On a neutron star, the gravity is so intense that any bump higher than a centimeter would crack the crystalline crust and sink down to the average surface level, almost immediately. The result is a surface smoother than any polished mirror, any machined ball bearing, any surface that human technology has ever produced or could ever produce. The gravity also bends light around the neutron star in ways that create strange visual effects for any hypothetical observer looking at the object from nearby in space. Because light follows curved paths near massive objects, according to general relativity, light from the far side of the neutron star can bend around and reach an observer looking at the front. This means that from any viewing angle, more than half of the neutron star's surface is visible at once, with the back curving into view around the edges of the sphere. The visual effect would be deeply strange, a sphere that seems to wrap around itself, showing more surface area than geometry would normally allow for any ordinary object. The temperature of a neutron star depends on its age, with newly formed ones being extremely hot, and older ones having cooled over millions of years of radiating energy into space. A young neutron star might have a surface temperature of 1,000,000 degrees or more, glowing brightly in X-rays that our instruments can detect from enormous distances across the galaxy. As the neutron star ages, it gradually cools, radiating away its thermal energy into the surrounding space until it reaches temperatures that might be merely thousands of degrees at the surface. Even an old, cooled neutron star remains far hotter than any surface on Earth. But the cooling process continues inexorably over the vast timescales involved. The size of a neutron star, roughly 20 kilometers across, means that you could theoretically drive across one in about 15 minutes at highway speeds if such a journey were somehow possible. This is about the distance from one side of a large city to the other, a span that seems modest for an object containing more mass than our entire sun held within it. The contrast between this small size and the enormous mass creates the extreme density that makes neutron stars so remarkable among all the objects astronomy has revealed to us. Everything about these objects exists at the extremes of what physics allows, pushing matter to conditions that cannot be replicated anywhere else. The formation of a neutron star occurs during the death of a massive star, when the core collapses under its own gravity after nuclear fusion can no longer provide the outward pressure needed for support. This collapse happens incredibly quickly, taking less than a second for the core to go from roughly the size of Earth to just 20 kilometers across in a catastrophic implosion. The speed of the collapse exceeds even the speed of sound within the collapsing material, creating a shock wave that rebounds outward and tears apart the outer layers of the star in a supernova explosion. What remains at the center, still and quiet after the explosion has passed, is the newly formed neutron star beginning its long existence, spinning in the darkness, The rapid spin of a pulsar traces directly back to this moment of formation, when the conservation of angular momentum caused the rotation rate to increase dramatically as the core shrank to such a tiny size. Any rotation the original stellar core possessed before collapse becomes amplified enormously as the material is compressed into such a small volume, like the ice skater pulling in arms to spin faster. A core that rotated once over the course of a month before collapse becomes a neutron star, spinning many times per second after the compression is complete and the new object settles into stability. The fastest pulsars have additional stories beyond this initial spin-up, but the basic mechanism explains why newly born pulsars rotate so rapidly from their very first moments. The pulsar we have been discussing, spinning 716 times per second, represents the extreme end of what is possible through this physics, and through additional processes that spin pulsars even faster. Its rotation is maintained against gradual slowing by the stability of the neutron star material, which can hold its shape and spin for billions of years without significant structural change. The object that creates the beam, the object that we detect from thousands of light years away, is this tiny, dense sphere of compressed matter spinning in the darkness of space between the scattered stars of our galaxy. Understanding that such objects exist changes how we think about matter, about stars, about what the universe can create through the relentless operation of physical law over cosmic time. The neutron star sits at the heart of everything we have discussed so far. The spinning object that creates the beam, the dense remnant that holds together despite incredible forces trying to tear it apart. Its properties determine the behavior of the pulsar, from the rotation rate to the beam intensity, to the gradual slowing that occurs over millions of years as energy radiates away. Everything remarkable about pulsars traces back to the remarkable nature of neutron stars themselves, these compressed remnants of stellar cores that exist nowhere else and behave like nothing else we have ever encountered. The neutron star is the engine that drives the lighthouse, the clock that keeps cosmic time, the anchor around which everything else about pulsars revolves. These objects were completely unknown to science until the late 1960s, when a graduate student noticed something strange in the data from a new radio telescope searching the sky for distant cosmic phenomena. That discovery, made almost by accident during observations intended for other purposes, revealed an entirely new class of objects that astronomers had not predicted or anticipated would exist. The story of how pulsars were first found, the initial confusion and excitement, the gradual realization of what these signals represented, forms an important part of understanding these objects and our relationship to them. That discovery is where our journey turns next, back to a field in Cambridge and the careful eyes of a young scientist examining miles of paper charts. The discovery of pulsars happened in England in 1967, at a time when radio astronomy was still relatively young and the sky at radio wavelengths remained largely unexplored territory. A new telescope had been constructed near Cambridge. Not a dish like many radio telescopes, but an array of wires and poles spread across several acres of an English field. The instrument was designed to study distant galaxies and quasars by looking for the twinkling effect that occurs when radio waves pass through the solar wind emanating from our sun outward into space. No one expected the telescope to discover an entirely new type of astronomical object, but science often delivers its most important findings through paths that were not anticipated at the start. A graduate student named Jocelyn Bell was responsible for much of the day-to-day operation and data analysis, spending long hours examining the paper chart recordings produced by the telescope during its observations. The telescope recorded its data as wiggly lines on long strips of paper that scrolled continuously as the instrument scanned across different parts of the radio sky above. Each day produced about 90 feet of paper covered in these recorded signals, and Bell reviewed all of it carefully, looking for the patterns that indicated interesting astronomical sources worthy of further investigation. It was tedious work requiring patience and attention, with most of the paper showing only noise and ordinary sources already known and catalogued by astronomers worldwide. In August of 1967, Bell noticed something unusual on one of these paper recordings, a small section of signal that did not fit any pattern she had seen before in her months of careful observation. The signal appeared as a bit of what she called scruff, a technical term that did not quite convey the significance of what had actually been recorded on that strip of paper that day. When she looked more closely and managed to capture the signal with better time resolution, using faster recording equipment, she discovered something surprising and unprecedented in the history of radio astronomy. The signal was pulsing regularly, with individual pulses arriving every 1.337 seconds, in a rhythm too precise to seem natural or coincidental. The regularity of the signal was deeply puzzling, because natural astronomical sources were not expected to produce such clock-like timing in their emissions reaching Earth from distant space. Stars flicker and vary, galaxies show complex patterns, quasars fluctuate unpredictably, but nothing in the known universe produced such steady, metronome-like pulses with such precise intervals between each arrival. The source kept perfect time, better than many human-made clocks, sending its signal across the void with a regularity that seemed almost artificial in its perfection. Bell and her supervisor, Anthony Hewish, considered various explanations for what might produce such an unusual and precisely timed signal from the depths of interstellar space far from Earth. One possibility they considered, at least half seriously, was that the signal might originate from an intelligent civilization somewhere in the galaxy, attempting to make contact with other beings. The team even labeled the source LGM-1, with the letters standing for Little Green Men, acknowledging the possibility, however remote, that this might be deliberate communication from alien technology. The idea was not entirely frivolous, given how unnatural the signal seemed, with its clock-like regularity, unlike anything produced by known astronomical processes or random natural phenomena. For a brief period, the possibility of extraterrestrial intelligence hung over the discovery, adding a strange tension to what was already an exciting and confusing finding for the young research team. However, Bell soon discovered additional similar sources in completely different parts of the sky, each pulsing at its own distinct rate, but sharing the same fundamental characteristic of remarkable regularity. Finding multiple sources scattered across the heavens made the alien hypothesis much less likely, because it would require multiple civilizations in different directions, all choosing to broadcast in similar ways simultaneously. The natural explanation became more attractive with each new source discovered, even though no one yet understood what natural process could produce such precise and regular pulsing from astronomical objects. By the end of 1967, 4 of these pulsing sources had been identified, enough to establish that a new class of astronomical object had genuinely been discovered by the Cambridge team. The announcement of the discovery came in February of 1968 through a paper published in the scientific journal Nature, revealing to the world that a new type of celestial object existed and could be detected. The term pulsar was coined shortly afterward by a journalist, combining the words pulse and star into a compact name that captured the essential characteristic of these newly discovered objects succinctly. The name stuck immediately and has been used ever since to describe these spinning, beaming remnants of dead stars scattered throughout our galaxy and beyond in other galaxies as well. Within months, astronomers around the world were searching for additional pulsars and trying to understand what physical process could explain their remarkable behavior and precise timing characteristics. The theoretical explanation came surprisingly quickly, with scientists proposing that pulsars were rapidly rotating neutron stars within just weeks of the public announcement of their discovery. The idea of neutron stars had been suggested decades earlier, in the 1930s, as a possible outcome when massive stars exhausted their fuel and collapsed under their own weight catastrophically. These hypothetical objects had remained purely theoretical until pulsars provided the first observational evidence that such extremely dense stellar remnants actually existed in the real universe beyond our mathematical models. The rapid rotation and strong magnetic field of a neutron star could naturally produce the lighthouse-like beam that swept across space with each rotation of the compact stellar corpse. Jocelyn Bell's contribution to the discovery was essential and undeniable, as she was the one who noticed the unusual signal and recognized its significance among the miles of data she reviewed. Her careful attention and willingness to investigate something that did not fit expected patterns led directly to one of the most important astronomical discoveries of the 20th century, worldwide. When the Nobel Prize in Physics was awarded in 1974 for the discovery of pulsars, it went to Anthony Hewish and Martin Ryle, but did not include Bell herself among the honorees. This omission has been widely criticized in the decades since, with many astronomers feeling that Bell deserved recognition for her central role in the actual discovery process that changed our understanding of stellar evolution. Bell herself has spoken graciously about the situation over the years, noting that the Nobel Committee may have followed traditional practices of crediting supervisors rather than students for discoveries made during doctoral research. She went on to have a distinguished career in astronomy, receiving numerous other honors and awards, recognizing her contributions to science and her role in discovering pulsars, specifically the first pulsar she detected, now known by its catalog designation PSRB 1919+21, continues to pulse regularly to this day. More than 50 years after Bell first noticed its signal on that strip of paper chart recording, every 1.337 seconds it completes another rotation and sends another sweep of its beam across the cosmos in the same pattern Bell first observed so long ago in that English field. The discovery opened an entirely new field of astronomy, with pulsar observations providing insights into physics that could not be studied in any laboratory on Earth due to the extreme conditions involved. These objects offered natural laboratories for testing theories of gravity, nuclear physics, and the behavior of matter under pressures and densities impossible to recreate artificially here on our planet. Thousands of pulsars have been discovered since that first detection in 1967, each one spinning and beaming in the darkness of space. Each one a remnant of a star that lived and died long ago. The Cambridge discovery revealed that the galaxy contains these cosmic lighthouses in abundance, spinning silently, except for the radio whispers they send across the light years to reach us. That first pulsar still rotates at the same rate it showed Bell in 1967. Its period so stable that any changes would take centuries or millennia to become noticeable to even the most precise measurements. The source that once might have been aliens turned out to be something in some ways more remarkable, a type of object that the universe creates naturally through stellar death and gravitational collapse. The little green men hypothesis faded away, but what replaced it was a deeper understanding of how stars end their lives and what remains behind when the nuclear fires go out permanently. The discovery at Cambridge opened a window onto processes that shape the galaxy itself, revealing objects born from violence but persisting in patient, steady rotation for ages beyond human comprehension or timescales. Understanding how these objects come to exist requires looking backward in time to the death of the massive stars that eventually become pulsars through catastrophic collapse and transformation. The journey from living star to spinning pulsar involves some of the most extreme events the universe produces, moments of collapse and rebirth that reshape matter at the most fundamental level possible. The story of how a pulsar comes to exist begins with a star much larger than our Sun, a massive ball of gas that burns through its nuclear fuel far more quickly than smaller, more modest stars like our own. These massive stars may contain 8 or 10 or even 20 times the mass of the Sun, and their greater weight creates greater pressure in their cores, driving nuclear reactions at faster rates. A star like our Sun will shine for about 10 billion years before exhausting its hydrogen fuel, but a massive star might burn through its supply in just a few million years, despite having much more fuel to begin with. The extra mass creates extra pressure, and the extra pressure creates extra heat, and the extra heat drives faster reactions that consume the available fuel much more rapidly. During most of a massive star's life, the energy released by nuclear fusion in its core creates an outward pressure that perfectly balances the inward pull of gravity, trying to compress the star. This balance, called hydrostatic equilibrium, keeps the star stable and allows it to shine steadily for as long as fuel remains available to power the nuclear reactions, generating that outward pressure. The star fuses hydrogen into helium in its core, and when the hydrogen runs low, it begins fusing helium into heavier elements like carbon and oxygen through different nuclear pathways. Each stage of fusion releases less energy than the previous one, and each stage lasts for a shorter time as the star burns through its remaining options ever more quickly. A massive star eventually develops a layered structure like an onion, with different elements being fused in different shells, surrounding the core as it produces ever heavier elements in succession. The outermost shell might still be fusing hydrogen, while deeper shells fuse helium, carbon, oxygen, and silicon in progressively hotter and denser regions closer to the stellar center. This process continues until the core begins producing iron, which represents a fundamental turning point in the star's evolution, because iron fusion does not release energy the way previous reactions did, freely. Instead, fusing iron atoms together requires adding energy rather than releasing it, which means the core can no longer generate the outward pressure needed to support the enormous weight of the star above it. When the iron core reaches a critical mass, roughly 1.5 times the mass of our Sun, concentrated in a region about the size of Earth, the balance that sustained the star for millions of years fails catastrophically within a single second. The core collapses inward at speeds approaching 1/4 of the speed of light, falling in on itself faster than any other process in the macroscopic universe, outside of black hole formation. The outer layers of the star, suddenly unsupported, begin falling inward as well, chasing the collapsing core toward the center of what was, moments ago, a stable and functioning star. This collapse happens so quickly that the star essentially falls in on itself before light could cross from one side to the other, faster than information can even travel through the stellar material. The collapsing core becomes denser and denser as more and more mass crushes into a smaller and smaller volume during these final fractions of a second. Electrons are pushed into protons, combining to form neutrons through a process that also releases ghostly particles called neutrinos that stream outward, carrying away enormous amounts of energy, invisibly. The core that was Earth-sized moments ago shrinks to the size of a city, perhaps 20 kilometers across, in less time than it takes a human heart to beat once. What stops the collapse is not any chemical or nuclear force, but rather the quantum mechanical properties of neutrons themselves, which resist being compressed beyond a certain density due to fundamental laws of physics. The collapsing outer layers of the star slam into this suddenly rigid core and rebound outward in a tremendous explosion called a supernova, one of the most energetic events in the entire universe after the Big Bang itself. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars, releasing more energy than the Sun will produce in its entire 10 billion year lifetime combined. The outer layers of the dead star are flung into space at thousands of kilometers per second, creating the beautiful expanding clouds we see as supernova remnants scattered throughout the galaxy today. But the core remains behind, a dense ball of neutrons just 20 kilometers across, yet containing more mass than the entire Sun compressed into that tiny volume. This neutron star is born, spinning rapidly, and the reason for this rapid rotation traces back to a simple principle of physics that applies to everything from figure skaters to collapsing stellar cores universally. The original star rotated slowly, perhaps completing one rotation every few weeks or months, as massive stars typically do during their normal hydrogen-burning lives in cosmic terms. When the core collapsed, from Earth-sized to city-sized, shrinking by a factor of thousands in radius, all that rotational motion had to go somewhere, according to the conservation of angular momentum. Just as a figure skater spins faster when they pull their arms close to their body, the collapsing core spins faster and faster as it shrinks, smaller and smaller. A star that rotated once a month before collapse might rotate dozens or hundreds of times per second after the core shrinks to neutron star dimensions through this conservation process. The mathematics are straightforward, but the results are dramatic, transforming a leisurely stellar rotation into the frantic spinning of a pulsar in a single moment of gravitational collapse. The fastest young pulsars can rotate more than 60 times per second immediately after formation, their surfaces moving at significant fractions of the speed of light from the very beginning. This initial spin rate depends on how fast the original star was rotating and exactly how much mass ends up in the final neutron star core after the explosion clears. The same collapse that speeds up the rotation also intensifies the magnetic field of the newly formed neutron star to extraordinary levels far beyond anything else in the universe. The original star had a magnetic field, perhaps similar in strength to the Sun's field, spread across a volume millions of kilometers in diameter during its normal stellar life. When that field gets compressed along with the stellar material into a volume only 20 kilometers across, the field strength increases by factors of billions, concentrating all that magnetic energy into a tiny space. The resulting magnetic field is typically about 1 trillion times stronger than Earth's field, strong enough to affect the motion of charged particles from enormous distances away. This combination of rapid rotation and intense magnetic field creates the conditions necessary for pulsar emission to occur and be detectable from light years away across the galaxy. The spinning magnetic field generates electric fields that accelerate charged particles to speeds very close to the speed of light, along the magnetic field lines extending outward from the stellar surface. These accelerated particles emit radiation as they move, producing beams that emerge from the magnetic poles and sweep through space as the star rotates beneath them. A pulsar is essentially a spinning magnet, but a magnet of such power that it can broadcast its presence across thousands of light years to reach our radio telescopes on Earth. Not every supernova produces a pulsar, because the most massive stars create cores too heavy to stabilize as neutron stars and instead collapse further into black holes from which no signal can escape. The boundary between stars that produce neutron stars and those that produce black holes lies somewhere around 20 to 25 times the mass of the Sun, though the exact limit depends on details of the explosion and the star's composition at the time of collapse. Stars below this limit leave behind spinning, pulsing neutron stars that can be detected for millions of years afterward, while stars above this limit vanish into black holes that emit no pulsar beams at all. The pulsars we detect represent the middle ground of stellar death, massive enough to collapse, but not so massive that the collapse continues past the neutron star phase entirely. The supernova explosion that creates a pulsar also leaves behind the expanding cloud of debris that we observe as a supernova remnant for thousands of years afterward. The Crab Nebula, one of the most famous objects in the sky, represents the remnant of a supernova that was observed on Earth in the year 1054 by Chinese and Japanese astronomers, who recorded its appearance. At the heart of that nebula sits the Crab Pulsar, still spinning 30 times per second, nearly 1,000 years after its violent birth, in full view of human observers in medieval times. The connection between the pulsar and its surrounding nebula provided early confirmation that pulsars really were the collapsed cores of exploded stars, as theorists had proposed immediately after their discovery. Every pulsar in the sky represents a star that died in this manner, collapsing and exploding to leave behind a spinning, magnetized remnant that broadcasts its presence across the cosmos. Some are young, like the Crab Pulsar, still surrounded by the glowing debris of their birth explosions, visible through telescopes from Earth today. Others are old, having spun for millions or billions of years, as their birth nebulae faded and dispersed into the interstellar medium long ago. Each one carries within its rotation the memory of a stellar collapse that happened in an instant, but created an object that will persist for ages beyond human reckoning or comprehension. The magnetic field that forms during this collapse deserves deeper exploration, for it shapes everything about how pulsars behave and how their beams sweep across the galaxy, reaching distant worlds. This field, compressed from stellar dimensions to neutron star size, creates a structure of invisible force that extends far beyond the tiny surface of the spinning star itself, outward into the surrounding space. The magnetic field of a pulsar extends outward from the neutron star's surface like an invisible architecture of force and energy that shapes the surrounding space for thousands of kilometers in every direction. This field is not something we can see directly, but its effects are visible in the radiation that pulsars produce and the behavior of particles caught within its influence near the spinning stellar remnant. The strength of a typical pulsar's magnetic field reaches about 1 trillion times the strength of Earth's magnetic field, a difference so vast that comparison becomes almost meaningless. Earth's field can deflect a compass needle and protect us from solar wind, but a pulsar's field can accelerate particles to nearly the speed of light itself. The shape of this magnetic field resembles the field of a simple bar magnet, with lines of force emerging from one magnetic pole and curving through space to re-enter at the opposite pole in continuous loops. This dipole structure, as scientists call it, creates a natural geometry that focuses energy toward the two polar regions where the field lines converge, most strongly near the stellar surface. The magnetic poles are not necessarily aligned with the rotation axis of the neutron star, and this misalignment is crucial for producing the pulsar phenomenon that makes these objects detectable at all. If the magnetic axis were perfectly aligned with the rotation axis, the beams would simply point in the same direction constantly, and no pulsing would occur as seen from any particular viewing angle. Instead, the magnetic axis is typically tilted at some angle relative to the spin axis, so the magnetic poles trace circles around the sky as the neutron star rotates beneath them continuously. This tilted configuration means the beams emerging from the magnetic poles sweep through space like the beams from a lighthouse, painting circles in the cosmic darkness with each rotation of the star. Only observers who happen to lie along the path of these sweeping beams will detect the pulsar, seeing regular flashes as the beam crosses their line of sight repeatedly. Many neutron stars probably exist whose beams never cross Earth's position, making them invisible to us despite rotating and beaming, just like the pulsars we can detect. The region around a pulsar, dominated by its magnetic field, is called the magnetosphere, extending outward to a boundary where the magnetic influence gives way to the ordinary interstellar medium beyond. For most pulsars, this magnetosphere reaches out a few thousand kilometers from the surface, a substantial region, though tiny compared to the distances between stars in the broader galaxy. Within this magnetosphere, the magnetic field controls everything, forcing charged particles to move along field lines rather than in straight paths through the space surrounding the neutron star. The field is so strong that it dominates the behavior of matter in ways that would be impossible to recreate in any laboratory on Earth with currently imaginable technology. Particles within the magnetosphere are accelerated to tremendous speeds by the electric fields that the rotating magnetic field generates through fundamental electromagnetic processes described by physics equations. A changing magnetic field creates an electric field, and a spinning magnetic field is constantly changing from the perspective of any fixed point in space around the rotating star. These induced electric fields pull electrons and positrons along the curved magnetic field lines, accelerating them to energies that would require the largest particle accelerators on Earth to achieve artificially. By the time these particles reach the regions near the magnetic poles, they are traveling at speeds exceeding 99% of the speed of light, routinely. When charged particles travel along curved paths at such extreme speeds, they emit radiation through a process called synchrotron emission, or curvature radiation, depending on the specific geometry of their motion. This radiation is beamed in the direction the particles are traveling, creating concentrated rays of energy rather than radiation spreading out evenly in all directions from the source location. The combined effect of many particles streaming along the field lines near each magnetic pole creates a beam of radiation that extends outward into space from each polar region simultaneously. These twin beams, emerging from opposite sides of the neutron star, are what we detect as pulses when one or both sweep across our line of sight during each rotation cycle. The beams contain radiation across a wide range of wavelengths, from radio waves through visible light and sometimes extending to X-rays and gamma rays for the most energetic pulsars in the galaxy. Most pulsars are detected primarily at radio wavelengths, which is why radio telescopes discovered them in the first place and remain the primary instruments for pulsar observation and study today. Some pulsars also emit strongly at higher energies, appearing as point sources of X-rays or gamma rays to space telescopes designed to detect these more energetic forms of light, invisible from Earth's surface. The Crab pulsar, for instance, has been detected across nearly the entire electromagnetic spectrum, from radio waves to gamma rays, making it one of the most thoroughly studied pulsars known anywhere. The energy carried away by these beams comes ultimately from the rotational energy of the spinning neutron star, which means that pulsars gradually slow down over time as they radiate away their spin energy continuously. This slowdown is usually very gradual, measured in tiny fractions of a second lost over years or decades of observation. But it is detectable with precise timing measurements accumulated over extended periods. The rate of slowdown tells astronomers about the strength of the magnetic field, because stronger fields produce more radiation and cause faster energy loss from the spinning system overall. Young pulsars with strong fields slow down relatively quickly, while older pulsars with weaker fields slow down much more gradually over longer time spans. The magnetic field of a pulsar is not perfectly smooth and uniform, but contains complexities and structures that affect the details of the emitted radiation in ways scientists are still working to fully understand and model. The beams themselves are not simple cones of uniform radiation, but contain substructure that produces the specific pulse profiles observed for each individual pulsar distinctively. Some pulsars show single peaks in their pulse profiles, while others show double peaks or more complex structures that repeat reliably with each rotation of the neutron star beneath them. These differences reflect differences in the magnetic field geometry and the distribution of radiating particles within the magnetosphere surrounding each particular spinning stellar remnant. The environment immediately around a pulsar's magnetic poles is one of the most extreme places in the universe, with electric fields strong enough to rip electrons from atoms, and magnetic fields strong enough to distort the shapes of atoms themselves. Fundamentally, in such fields, ordinary matter cannot exist in familiar forms, and even the vacuum of space behaves differently than it does in the weaker fields we experience in everyday life on Earth. The particles being accelerated in these regions experience forces and energies that test the limits of our physical theories, providing natural laboratories for studying physics under conditions impossible to create artificially anywhere humans can reach currently. The magnetic field also interacts with the thin atmosphere that may exist on the neutron star's surface, channeling any material present toward the magnetic poles, where it can contribute to the emission process. Matter falling onto a neutron star from a companion star in a binary system will follow the magnetic field lines toward the poles, creating hotspots where the infalling material releases its energy as X-rays visible from great distances across the galaxy. These X-ray pulsars, powered by accretion rather than rotation, represent a different variety of pulsar phenomenon with their own distinctive characteristics and behaviors for astronomers to study. The magnetic field is central to both types, shaping the flow of energy and matter in all cases involving neutron stars. The field extends far beyond the neutron star surface, but the surface itself is equally remarkable, a landscape where gravity and density reach values beyond anything else directly observable in the universe today. This surface, made of compressed matter in forms that exist nowhere else, provides the foundation from which the magnetic field emerges, and the beams are launched across interstellar distances. The conditions there are so extreme that our ordinary intuitions about matter, gravity, and scale fail completely when trying to envision what this environment would actually be like up close. The surface of a neutron star represents one of the most extreme environments in the entire universe, a landscape shaped by gravitational forces billions of times stronger than anything on Earth. This surface is not made of ordinary matter in any form we would recognize, but rather consists of material compressed to densities so great that familiar atomic structure has been crushed out of existence entirely. A neutron star surface exists at the boundary between the intense interior and the near vacuum of space around it, a thin crust covering the exotic matter beneath it completely. Standing on this surface would be impossible for any structure made of ordinary matter, which would be crushed flat instantly by the overwhelming gravitational pull toward the center. The gravity at the surface of a typical neutron star is about 200 billion times stronger than the gravity we feel on Earth's surface, holding us in place daily. An object dropped from a height of 1 meter above this surface would accelerate so rapidly that it would strike the surface traveling at about 2,000 kilometers per second, or roughly 6% of the speed of light. For comparison, the fastest spacecraft humanity has ever built travel at only about 17 kilometers per second, more than 100 times slower than this falling object would achieve in a single meter of descent. The gravitational acceleration is so extreme that concepts like falling or dropping become almost meaningless at scales we can intuitively grasp or picture. This extreme gravity has profound effects on the shape of the surface itself, forcing it into almost perfect spherical smoothness without significant features or variations across its expanse. Any mountain or elevation that tried to form on a neutron star surface would be crushed flat by its own weight under the immense gravitational pull pressing down upon it continuously. The tallest possible mountains on a neutron star might be only a few centimeters high, perhaps no taller than a small coin standing on its edge, at most. The crust simply cannot support larger structures against the relentless force of gravity, that flattens everything toward perfect spherical symmetry with remarkable precision. The crust itself is made primarily of iron nuclei, the same element that forms Earth's core, but arranged in a crystalline lattice structure, compressed to incredible densities, unlike anything found on our planet. This iron lattice is about 1 billion times denser than iron on Earth, packed so tightly that the nuclei are squeezed together as closely as nuclear forces will allow under such pressure. The crust is relatively thin, perhaps only about 1 kilometer thick, sitting atop the even denser neutron-rich fluid that makes up the bulk of the stellar interior beneath it. This thin shell of solid material represents the only part of the neutron star that has any resemblance to ordinary solid matter at all, however distorted. Below the crust, the neutron star interior consists primarily of neutrons packed together at densities comparable to atomic nuclei, but extending across a region 20 kilometers in diameter, continuously. This neutron fluid behaves in ways that ordinary fluids do not, possibly becoming superfluid at the temperatures found deep within neutron stars, where quantum effects dominate behavior completely. A superfluid flows without any friction or resistance, allowing it to maintain rotation patterns and currents indefinitely without losing energy to internal viscosity over time. The existence of such a superfluid interior may explain certain peculiar behaviors observed in some pulsars, including the sudden spin-up events called glitches that occur occasionally. The surface temperature of a young neutron star can exceed 1 million degrees, hot enough to glow brightly in X-rays even without any external heating source, providing additional energy input. This heat is left over from the neutron star's violent formation in the supernova explosion, and it gradually radiates away over millions of years as the star cools slowly in the cold of space. Older neutron stars have cooled substantially, though they may still have surface temperatures of hundreds of thousands of degrees, even after billions of years of cooling in the dark void. The cooling rate depends on the star's mass, composition, and various exotic physics processes that may occur deep within its dense interior regions. Light behaves strangely near a neutron star surface, due to the extreme gravitational field bending the paths that photons follow through the curved space surrounding the compact object. This gravitational lensing effect is strong enough that an observer near a neutron star could see more than half of the surface at once. Because light from the far side bends around the curved space-time toward the observer's eyes, the surface appears to wrap around toward you, with parts that should be hidden behind the curve of the sphere becoming visible due to the bending of light in the intense gravitational field present everywhere near the star. This effect would make the neutron star appear larger than its physical size and would create strange visual distortions unlike anything we experience in ordinary environments on Earth. Time itself runs slower on the surface of a neutron star compared to distant locations far from its gravitational influence, an effect predicted by Einstein's general theory of relativity and measurable in principle. The gravitational time dilation at a neutron star surface amounts to about 30%, meaning that time passes about 30% slower there than it does for observers far away from any massive body. An hour spent on the neutron star surface, if such a visit was somehow possible, would correspond to about 1 hour and 20 minutes passing for distant observers watching from space safely. This relativistic effect is real and would apply to any clock or physical process occurring at the surface of such a dense, massive, compact object anywhere in the universe. The thin atmosphere that may exist above the crust, if present at all, consists of the lightest elements that can remain gravitationally bound to the surface against the intense radiation pressure, trying to push them away. This atmosphere might be only a few centimeters thick, made primarily of hydrogen or helium, depending on the history and environment of the particular neutron star in question. At any given time, the atmosphere affects the spectrum of radiation emitted from the surface, providing clues about the composition and conditions at this otherwise unreachable location, far across the galaxy from our observational position. Studying these atmospheric signatures helps scientists understand the physics occurring at the neutron star surface, despite being unable to visit it directly in any foreseeable future. The crust of a neutron star is not perfectly rigid, but can crack and shift under certain conditions, producing events called starquakes that briefly affect the pulsar's rotation rate noticeably. When the neutron star spins down gradually over time, the decreasing centrifugal force allows the equator to shrink slightly, while the crust resists this change through its structural rigidity temporarily. Eventually, the stress becomes too great and the crust cracks, adjusting suddenly to a more spherical shape and causing a tiny but measurable change in the rotation rate of the pulsar immediately. These glitches, as they are called, have been observed in many pulsars and provide information about the physical properties of the crust and interior structure of these exotic objects. The Vela pulsar is particularly famous for exhibiting frequent glitches, having shown more than 20 such events since regular observations began tracking its behavior over decades of continuous monitoring. Each glitch represents a sudden spin-up, with the pulsar rotating slightly faster immediately after the event, before gradually returning toward its previous slowdown trend over subsequent days and weeks. The physics of these glitches involves both the solid crust and the superfluid interior, with the two components interacting in complex ways that scientists are still working to fully understand theoretically. These events provide rare windows into the internal structure of neutron stars, revealing information that would otherwise remain hidden from external observation entirely. The surface and interior of a neutron star together create the physical foundation that allows pulsars to spin, beam, and persist for millions of years across the galaxy in such remarkable abundance. This extreme object, no larger than a city yet more massive than the Sun, generates the magnetic fields and rotation that make pulsar detection possible from enormous distances across the cosmos. Among all the pulsars in the sky, some spin far faster than others, having been accelerated to remarkable rotation rates through processes that add energy rather than letting it drain away gradually over cosmic time spans. The fastest spinning pulsars in the universe rotate at speeds that seem almost impossible for objects containing more mass than the entire Sun packed into such small volumes of space. These millisecond pulsars, as they are called, complete hundreds of rotations every single second, their surfaces moving at significant fractions of the speed of light, continuously without interruption. The fastest one, currently known, spins 716 times per second, a rotation rate so rapid that each complete revolution takes only about 1.4 milliseconds to finish entirely. This pulsar, designated PSRJ 1748-2446 AD, holds the record for the fastest confirmed rotation of any known object in the entire universe studied by astronomers. The existence of these extremely fast pulsars presented a puzzle when they were first discovered. Because pulsars are supposed to slow down over time as they lose rotational energy to their beamed radiation continuously. A pulsar born spinning 60 times per second in a supernova should gradually slow down over millions of years, not speed up to spin hundreds of times faster than it started initially. Young pulsars are fast, and old pulsars are slow, according to the simple evolutionary picture. So finding old pulsars spinning faster than young ones seemed to contradict the basic physics of pulsar evolution entirely. The solution to this puzzle involves companion stars and a process of rejuvenation that can spin an old, slowed pulsar back up to extraordinary rotation rates. Many millisecond pulsars are found in binary systems, orbiting together with companion stars that have transferred mass onto the neutron star over long periods of cosmic time in the past. When a companion star expands during its evolution, material from its outer layers can flow toward the neutron star and form a disk of gas spiraling inward toward the surface. Gradually, this infalling material carries angular momentum, rotational energy that gets transferred to the neutron star as the matter settles onto its surface continuously over millions of years of accretion. Bit by bit, the infalling gas spins the pulsar faster and faster, gradually accelerating its rotation despite the natural tendency to slow down from energy loss to radiation. This process, called recycling, can continue for millions or even billions of years, as long as the companion star keeps supplying material to the accretion disk, feeding the neutron star at its center. By the time the companion is exhausted and the accretion stops, the pulsar may be spinning hundreds of times per second, far faster than it rotated when first born in the original supernova explosion. The recycled pulsar is old in terms of its age since formation, but young in terms of its rapid rotation rate, having been given a second life by its companion star's donation of angular momentum over cosmic time. These rejuvenated pulsars can spin for billions of years more before slowing down significantly. Their weak magnetic fields causing only minimal energy loss per rotation, compared to younger, more strongly magnetized pulsars. The companion stars in these systems are often white dwarfs, the dense remnants of stars less massive than those producing neutron stars, left behind after the mass transfer phase finally concludes. The original companion was once a normal star that expanded and donated material to the pulsar, eventually leaving behind only its core as a white dwarf in orbit with a spun-up neutron star. These binary millisecond pulsar systems provide beautiful examples of stellar evolution in action, with both components being stellar remnants orbiting each other in gravitationally bound pairs perpetually. The orbital periods can range from hours to weeks, depending on the separation between the two compact objects in each particular system configuration. The fastest pulsar, spinning 716 times per second, was discovered in a globular cluster called Tarzan 5, a dense, spherical collection of old stars orbiting the center of our Milky Way galaxy. Globular clusters are ideal environments for creating millisecond pulsars because the high stellar density leads to frequent encounters between stars that can capture and exchange companions readily. A neutron star might acquire a new companion through gravitational capture, begin accreting and spinning up, then lose that companion and acquire another one in a continuing cycle of interaction. Tarzan 5 contains many millisecond pulsars, more than almost any other globular cluster known, providing a laboratory for studying these objects in abundance within a single stellar system. At 716 rotations per second, the surface of this fastest pulsar at its equator moves at about 70,000 kilometers per second, or roughly 24% of the speed of light. Incredibly, material at the equator experiences centrifugal forces that would tear it away from the surface, if not for the immense gravitational pull holding everything together against this outward tendency. The balance between gravity pulling inward and centrifugal force pushing outward limits how fast a neutron star can possibly spin before it would fly apart into pieces, catastrophically. The fastest millisecond pulsars approach, but do not exceed this theoretical limit, spinning nearly as fast as physics allows, while remaining structurally intact and stable. The magnetic fields of millisecond pulsars are typically much weaker than those of young, ordinary pulsars. Having decayed over the billions of years since these neutron stars first formed in ancient supernovae, a young pulsar might have a magnetic field of 1 trillion times Earth's field, while a millisecond pulsar typically has a field only 1 billion times Earth's field. Still enormous, but much weaker comparatively. This weaker field means less energy is lost to radiation with each rotation, allowing the millisecond pulsar to maintain its rapid spin for much longer than a strongly magnetized young pulsar could possibly manage. The combination of weak field and fast spin makes millisecond pulsars among the most stable rotators in the universe. Their timing precision exceeded by nothing else in the natural cosmos anywhere. The discovery of millisecond pulsars in the 1980s revealed that pulsar evolution is not simply a one-way journey from fast to slow, but can involve revival and acceleration under the right circumstances. The first millisecond pulsar discovered, rotating 642 times per second, was found in 1982 and immediately challenged the existing understanding of how pulsars behaved over cosmic time spans. Today, hundreds of millisecond pulsars are known, found both in binary systems and as isolated objects whose companions have been completely evaporated or disrupted by the pulsar's energy over long time periods. Some of these isolated millisecond pulsars are called black widows or redbacks because they have consumed or destroyed their companion stars that originally spun them up so dramatically. The recycling process that creates millisecond pulsars connects them to another class of objects called X-ray binaries, which are actively accreting neutron stars surrounded by disks of hot gas emitting X-rays copiously today. These X-ray binaries represent the spinning up phase of the process, with material currently flowing onto the neutron star and gradually increasing its rotation rate in real time as astronomers observe. Some X-ray binaries have been observed to transition back and forth between accreting states and radio pulsar states, switching modes as the accretion rate varies from external observation perspectives. These transitional millisecond pulsars provide direct evidence that accretion really does spin up pulsars, catching the process in action rather than inferring it from circumstantial evidence alone. The existence of pulsars spinning 700 times per second tells us something profound about the strength and rigidity of the matter making up a neutron star under such extreme conditions and forces. Ordinary matter would fly apart at a tiny fraction of these rotation rates, unable to withstand the centrifugal forces generated by such rapid spinning in any structural configuration. Only the immense density and strong nuclear forces within neutron star matter allow these objects to hold together while spinning so incredibly fast without disruption or destruction. The fastest pulsars push the limits of what is physically possible, demonstrating how matter behaves under conditions found nowhere else in the universe that we can directly observe today. The remarkable stability of millisecond pulsar rotation makes them extraordinarily useful as precision tools for testing fundamental physics and probing the universe in ways no other objects can match. Their steady tick, maintained over billions of rotations without significant variation, exceeds the precision of the best atomic clocks humanity has ever constructed artificially here on Earth today. The precision of pulsar timing represents one of the most remarkable phenomena in all of nature, with these spinning dead stars keeping time more accurately than any mechanical or electronic clock humans have ever constructed. Millisecond pulsars, in particular, rotate with such stability that their pulse arrival times can be predicted with precision, better than 1 microsecond over spans of many years of continuous observation. This means that if you know when a pulse arrived today, you can calculate when pulses arrived years ago, or will arrive years from now, with almost perfect accuracy, reliably. No pendulum, quartz crystal, or even atomic clock maintains such consistent timing over such long periods as these natural cosmic chronometers spinning in the depths of space. Scientists measure pulsar timing by recording exactly when each pulse arrives at Earth, comparing these measured arrival times against predictions calculated from models of the pulsar's rotation and motion through space relative to our planet. Any discrepancy between predicted and actual arrival times contains information about something affecting the pulsar, the space between it and Earth, or our own planet's motion through the solar system in its annual orbit. By carefully analyzing these tiny discrepancies, astronomers can detect effects too subtle to measure by any other means available to scientific investigation currently. Pulsar timing has become one of the most powerful tools in all of astronomy for testing physics and exploring the universe around us comprehensively. The stability of pulsar timing relies on the enormous angular momentum stored in the spinning neutron star, a reservoir of rotational energy so vast that small perturbations cannot significantly affect the overall rotation rate over short time spans. A neutron star might contain a solar mass, spinning dozens or hundreds of times per second, representing an almost inconceivable amount of rotational energy locked into this tiny, dense object spinning in the void. Any force that tried to speed up or slow down this rotation would need to overcome this tremendous angular momentum, which acts like a flywheel maintaining steady rotation against external influences effectively. The result is a natural timekeeper that drifts less than 1 second over tens of millions of years of continuous operation without intervention. Using pulsar timing, scientists have conducted some of the most precise tests of Einstein's theory of general relativity ever performed, exploring how gravity behaves under conditions far more extreme than any we can create on Earth. The first major success came from the Hulse-Taylor binary pulsar, discovered in 1974, which consists of 2 neutron stars orbiting each other closely in a gravitational embrace. By timing the pulsar's signals over many years, Astronomers measured the slow decay of the orbit as gravitational waves carried energy away from the system continuously and irreversibly. The rate of orbital decay matched Einstein's predictions to better than 1% accuracy, providing the first indirect evidence that gravitational waves really existed as general relativity required. Gravitational waves are ripples in the fabric of space-time itself, created when massive objects accelerate and sending disturbances outward at the speed of light through the cosmos infinitely. Einstein predicted these waves in 1916, but they are so weak that direct detection did not occur until 2015, almost a century after the original theoretical prediction was made. The Hulse-Taylor binary pulsar provided indirect confirmation decades earlier, showing that the orbit was losing energy at exactly the rate gravitational wave emission would require, according to general relativity calculations. Russell Hulse and Joseph Taylor received the Nobel Prize in Physics in 1993 for this discovery and its implications for confirming fundamental gravitational physics experimentally. Today, arrays of pulsars are being used to directly detect gravitational waves passing through our galaxy, turning the network of millisecond pulsars scattered across the sky into a galaxy-sized gravitational wave detector. These pulsar timing arrays, as they are called, work by looking for correlated changes in the arrival times of pulses from many different pulsars distributed across wide regions of the sky. If a gravitational wave passes through the galaxy, it will stretch and squeeze space-time slightly, affecting the distances between Earth and the various pulsars in subtle but correlated ways detectable through careful analysis. The effect is incredibly small, changing pulse arrival times by perhaps a few nanoseconds. But with years of data from many pulsars, the signal can emerge from the noise. In 2023, pulsar timing arrays reported strong evidence for a background of gravitational waves permeating the universe, a constant rumble of space-time disturbance coming from all directions equally and continuously. This gravitational wave background is thought to originate from millions of supermassive black hole pairs throughout the universe, each pair slowly spiraling together and emitting gravitational waves as they approach eventual merger. The combined effect of all these distant sources creates a low-frequency hum of gravitational radiation that pulsar timing arrays are now sensitive enough to detect through patient observation over decades. This discovery opened a new window onto the universe, revealing information that only gravitational waves can carry to us from distant sources across cosmic time. The precision of pulsar timing has also been proposed as a navigation system for spacecraft traveling far from Earth, where ordinary radio navigation becomes impractical due to signal travel times and other limitations. By measuring the arrival times of pulses from several known pulsars, a spacecraft could determine its position in space using the pulsars as navigation beacons, much like GPS satellites serve that function for devices on Earth. Each pulsar has a unique timing signature, a fingerprint of period derivative, and position in the sky that distinguishes it from all other pulsars uniquely and permanently. A spacecraft computer could compare measured pulse arrivals against expected arrivals to calculate its three-dimensional position anywhere in the solar system or beyond. NASA has tested this concept using X-ray observations of pulsars, demonstrating that autonomous navigation using pulsar timing is technically feasible for future deep space missions to distant planets and beyond. The X-ray timing instrument on the International Space Station successfully demonstrated autonomous position determination using millisecond pulsar observations during initial testing and verification runs. While the system is not yet precise enough to replace conventional navigation for most missions, continued development could lead to practical pulsar-based navigation for spacecraft traveling to the outer solar system or interstellar space, eventually. The ancient spinning stars could guide future explorers, just as literal stars guided sailors across Earth's oceans for thousands of years of human seafaring history. The long-term timing of pulsars also reveals their gradual slowdown, the steady loss of rotational energy that will eventually cause all pulsars to fade below detectability over sufficiently long time spans. By measuring exactly how much the rotation period increases over time, astronomers can calculate how long the pulsar has been spinning and estimate its age since formation in the original supernova event. Young pulsars slow down relatively quickly because their strong magnetic fields cause rapid energy loss, while old millisecond pulsars slow so gradually that their periods are nearly constant over human timescales of observation and measurement. This timing information helps construct the evolutionary history of each individual pulsar, tracing its journey from violent birth to gradual decline over cosmic ages. The pulse profiles themselves, the shapes of the pulses as they arrive at Earth, contain information about the geometry of the magnetic field and the emission regions near the neutron star's surface, far away. Different pulsars show different profile shapes, from simple single peaks to complex structures with multiple components that repeat precisely with each rotation of the underlying neutron star. These profiles remain remarkably stable over time for most pulsars, maintaining their distinctive shapes year after year as billions of rotations occur beneath them steadily. Any changes in profile shape could indicate changes in the emission region or magnetosphere, providing clues about processes occurring on or near the neutron star surface. Pulsar timing connects these spinning dead stars to some of the deepest questions in physics, from the nature of gravity to the structure of space-time itself across cosmic distances. The precision these objects provide has no parallel elsewhere in nature, making them invaluable tools that complement human-built instruments for testing our understanding of the universe. Among the thousands of known pulsars, certain individuals stand out for their unique characteristics, extreme properties, or special circumstances that have taught us particularly important lessons about these remarkable objects spinning in the darkness between the stars. Among all the pulsars discovered throughout the galaxy, certain individuals have achieved a kind of fame within the astronomical community for what they have revealed about the nature of these spinning stellar remnants. Each notable pulsar has its own story, its own distinctive properties, and its own contributions to our understanding of neutron star physics and stellar evolution broadly. The Crab pulsar holds a special place among these famous individuals because we know exactly when it was born. Watching over it since before the supernova that created it was even observed by human eyes on Earth. This pulsar sits at the heart of the Crab Nebula, still young at less than 1,000 years old, energetic and active in ways that older pulsars cannot match anymore. The supernova that created the Crab pulsar exploded on the 4th of July in the year 1054, an event recorded by Chinese and Japanese astronomers who noted a bright new star appearing in the constellation we call Taurus today. The guest star, as they called it, was bright enough to be visible in daylight for several weeks and remained visible at night for nearly 2 years before fading below naked eye visibility permanently. The expanding debris from this explosion forms the Crab Nebula, one of the most studied and photographed objects in the sky, its filaments still rushing outward at over 1,000 kilometers per second today. At the center of this expanding cloud sits the Pulsar, the collapsed core that survived the explosion and has been spinning ever since that July day, nearly a millennium ago now. The Crab Pulsar rotates about 30 times per second, completing one full revolution in approximately 33 milliseconds, as it sweeps its beams through the surrounding nebula and beyond. This is fast for an ordinary pulsar, but slow compared to the millisecond pulsars that have been recycled by companion star accretion over much longer evolutionary timescales than the Crab has experienced yet. The pulsar is slowing down at a measurable rate, losing about 36 nanoseconds from its period every day as rotational energy drains away into the surrounding nebula continuously and permanently. This energy loss powers the continued glow of the Crab Nebula, with the pulsar's rotational energy being converted into the light and radiation we observe from the nebula today, still expanding. The Crab Pulsar was the first pulsar detected at wavelengths beyond radio, seen in visible light in 1969, when astronomers pointed optical telescopes at its position at the nebula's center carefully. The pulsar appears as a moderately bright star in optical images, but high-speed cameras reveal that it blinks on and off 30 times per second, in sync with the radio pulses arriving from the same direction. This was a crucial discovery because it confirmed that the radio pulses and optical pulses came from the same rotating source, a spinning neutron star producing radiation across multiple wavelength bands simultaneously. Since then, the Crab has been detected in X-rays and gamma rays as well, making it one of the few pulsars seen across essentially the entire electromagnetic spectrum completely. The Vela pulsar, located in the southern sky in the constellation Vela, is another famous individual, known particularly for its frequent and dramatic glitches that interrupt its otherwise steady rotation periodically. This pulsar is somewhat older than the Crab, having formed about 11,000 years ago in a supernova, whose remnant still surrounds it as an expanding bubble of hot gas visible to X-ray telescopes today. Vela rotates about 11 times per second, much slower than the Crab, and is slowing down gradually, as all pulsars do through the continuous loss of rotational energy to radiation emission outward. But occasionally, about once every few years on average, the Vela pulsar suddenly speeds up slightly in a glitch that scientists are still working to fully explain, theoretically. These glitches involve sudden increases in the rotation rate, amounting to a few parts per million. Tiny changes in absolute terms, but easily detectable with precise timing observations accumulated over years. The leading explanation involves the superfluid interior of the neutron star, which may rotate slightly faster than the solid crust due to differences in how they respond to the gradual slowdown. When the difference becomes too great, angular momentum suddenly transfers from the faster interior to the slower crust, causing the observed spin-up visible in timing measurements from Earth. The recovery after a glitch takes weeks or months as the system gradually relaxes back towards its previous state before the disruption occurred. Unexpectedly, the first pulsar ever discovered, PSRB 1919 plus 21, continues to pulse regularly more than 50 years after Jocelyn Bell first noticed its signal on a paper chart recording in that English field. This pulsar rotates once every 1.337 seconds, a relatively slow rotation rate that made its periodic signal easier to identify as something unusual and worthy of further investigation initially. The pulsar is located about 2,300 light-years from Earth, in the direction of the constellation Vulpecula. Too faint to see with optical telescopes, but readily detectable at radio wavelengths, with modest equipment today. Every astronomy student learns about this pulsar as the first of its kind discovered, the object that revealed an entirely new class of astronomical phenomena to human knowledge, permanently. The double pulsar, discovered in 2003, represents something extraordinary even among pulsars, because it consists of two pulsars orbiting each other in a tight gravitational embrace. This system, designated PSRJ0737-3039, contains two neutron stars orbiting each other every 2.4 hours, closer than any other known double neutron star system anywhere. Both neutron stars are pulsars, though one is much brighter than the other, and both beams sweep across Earth during each orbit, providing an unprecedented laboratory for testing gravity. The rapid orbit causes measurable relativistic effects, including orbital decay, precession, and time dilation, all matching general relativity predictions with extraordinary precision over years of careful observation. The double pulsar allows tests of gravity in the strong field regime, where Einstein's theory makes distinct predictions that differ from simpler Newtonian gravity significantly. By timing both pulsars independently and tracking their orbital motion precisely, scientists have verified multiple predictions of general relativity to high precision simultaneously, using the same system. The orbit is decaying due to gravitational wave emission at exactly the rate Einstein's equations predict, confirming once again that gravitational waves carry energy away from orbiting massive objects continuously. In about 85 million years, these two neutron stars will spiral together and merge in a cataclysmic collision, visible across the universe in gravitational waves and electromagnetic radiation alike, dramatically. Some pulsars are known primarily through X-rays rather than radio waves, their emission powered by accretion from companion stars rather than pure rotation of magnetic fields. These X-ray pulsars include some of the first X-ray sources discovered in the sky. Their pulsed emission, revealing the presence of spinning neutron stars at their centers during early X-ray astronomy explorations. The accretion process channels matter toward the magnetic poles, creating hotspots that emit X-rays as the material releases its gravitational energy upon striking the neutron star surface. Finally, as the neutron star rotates, these hotspots come into and out of view, producing the regular pulsations that identify these objects as pulsars despite their different emission mechanism compared to rotation-powered radio pulsars. Each pulsar is an individual with its own rotation rate, magnetic field strength, age, environment, and observational history, distinguishing it from all other pulsars in the known catalogue of thousands. Some are young and energetic, still surrounded by the glowing debris of their birth explosions, visible through telescopes today. Others are old and quiet, having spun for billions of years since ancient supernovae, whose remnants have long since faded and dispersed into the interstellar medium of the galaxy completely. Some orbit companions, while others spin alone in the darkness between the stars. Together, they form a population that reveals the full range of what neutron stars can be across cosmic time and evolutionary pathways throughout our galaxy and others beyond. Many pulsars do not spin in isolation, but share their cosmic journey with companion stars, bound together by gravity and influencing each other's evolution through mass transfer, tidal forces, and eventual spectacular mergers releasing enormous energy dramatically. Binary pulsars, those that orbit companion stars of various types, provide some of the most valuable laboratories for testing physics and understanding stellar evolution available anywhere in the universe today. The companion might be a white dwarf, the compact core of a sun-like star that has shed its outer layers and left behind only its dense central region. Or the companion might be another neutron star, creating a double neutron star system where both objects are the collapsed remnants of massive stars that died in supernovae long ago. Some pulsars even orbit ordinary stars that are still fusing hydrogen in their cores, though these are less common and represent earlier stages in the evolutionary paths that create millisecond pulsars. The first binary pulsar discovered was the Hulse-Taylor pulsar in 1974, found by Russell Hulse and Joseph Taylor during a systematic search for new pulsars using the Arecibo radio telescope in Puerto Rico carefully. The pulsar's timing showed periodic variations that revealed it was orbiting something massive, completing one orbit every 7.75 hours around an unseen companion in close gravitational embrace. Further analysis confirmed that the companion was another neutron star, making this the first known double neutron star system and opening an entirely new field of gravitational physics research immediately. Hulse and Taylor recognized the potential of this system for testing general relativity and began the long-term timing program that would eventually earn them the Nobel Prize. The orbital period of the Hulse-Taylor system decreases by about 76 microseconds every year due to energy loss from gravitational wave emission, as Einstein's theory predicts should occur continuously. This decrease means the two neutron stars are slowly spiraling closer together, their orbit shrinking imperceptibly on human timescales, but measurably over decades of patient observation and careful data collection. The measured rate of orbital decay matches the general relativity prediction to better than 0.5% accuracy. A stunning confirmation of Einstein's theory, under conditions far more extreme than any laboratory test could achieve. This indirect detection of gravitational wave emission preceded the direct detection by LIGO by more than 40 years, demonstrating that the waves Einstein predicted really exist and carry energy. The double neutron star systems will not remain binary forever, as the continued orbital decay will eventually bring the two compact objects close enough to merge in a cataclysmic collision millions of years in the future. The merger of two neutron stars releases enormous energy, producing gravitational waves strong enough to be detected across billions of light years and electromagnetic radiation visible across the entire spectrum, from radio to gamma rays. In August of 2017, the LIGO and Virgo gravitational wave detectors registered the signal from two merging neutron stars in a galaxy 130 million light-years away. The first such merger directly observed by humanity. Telescopes around the world and in space observed the accompanying flash of light, confirming the connection between gravitational wave sources and electromagnetic events predicted by theorists for decades previously. This merger event, designated GW170817, produced evidence that neutron star collisions are a major source of heavy elements like gold, platinum, and uranium in the universe today. The merger creates conditions hot and dense enough to build these heavy atoms through rapid neutron capture, a nuclear process that cannot occur in ordinary stellar environments anywhere else in the cosmos. The gold in jewelry worn today, the platinum in catalytic converters, the uranium in nuclear reactors may all trace their origins to ancient neutron star mergers that occurred billions of years before our solar system formed. Pulsars that eventually merge thus play a role in creating the heavy elements that make technology and even life possible on Earth today. Binary systems with pulsars come in many varieties beyond the double neutron star configuration that produces these spectacular mergers, eventually over cosmic time. Many millisecond pulsars orbit white dwarf companions, the remnants of the stars that donated mass and angular momentum during the recycling process that spun the pulsars up to their current rapid rotation rates. These systems are generally stable, with the white dwarf and pulsar orbiting each other for billions of years without significant evolution or change in their configuration anymore. The orbital periods range from hours to weeks depending on the separation, with closer systems showing measurable relativistic effects, while wider systems appear almost Newtonian in their behavior. Some binary pulsars have evaporated their companions almost entirely, earning them colorful names like black widows and redbacks, based on the spider species known for consuming their mates after reproduction. These pulsars emit intense radiation and particle winds that heat and ablate the companion star, slowly stripping away its outer layers and reducing its mass over millions of years progressively. The companion in these systems is typically a very low-mass star, sometimes only a few % of the Sun's mass, being slowly consumed by the energetic pulsar that once received matter from its now diminishing partner in an ironic reversal of roles. Eventually, the companion may be reduced to a planetary mass object or disappear entirely, leaving the pulsar spinning alone in space where a binary once existed together. The Black Widow pulsars represent an extreme endpoint of binary evolution, where the pulsar has become so energetic that it destroys the very companion that gave it new life through the recycling process long ago. The original companion was likely a normal star that overflowed its outer layers onto the neutron star, spinning it up to millisecond periods over millions of years of steady mass transfer and angular momentum exchange. Once the mass transfer ended, the now rapidly spinning pulsar turned its intense radiation on the remaining companion, beginning the slow process of evaporation that continues today in these remarkable binary systems. The pulsar essentially consumes its partner after benefiting from the relationship, earning the Black Widow name from astronomers who noticed the parallel to spider behavior in the natural world. Redback pulsars are similar to Black Widows, but have more massive companions, typically around a third of the Sun's mass, that are being irradiated but not yet completely evaporated by the pulsar's energetic emission. These systems seem to represent an intermediate stage in the evolution toward black widow status, with the companion still substantial enough to survive the pulsar's assault for now. Some redbacks switch between states, sometimes appearing as X-ray binaries when matter flows from the companion onto the pulsar, and sometimes appearing as radio pulsars when the mass transfer stops temporarily. This switching behavior provides direct evidence of the connection between accreting X-ray sources and radio pulsars that theory had long predicted should exist. The variety of binary pulsar systems provides windows into different stages of stellar and binary evolution that would otherwise be impossible to observe directly over human timescales practically. We cannot watch a single system evolve from initial binary to mass transfer to millisecond pulsar to black widow, because the process takes hundreds of millions of years to complete fully. Instead, we observe many different systems at different stages and piece together the evolutionary story from this snapshot collection of varying ages and configurations. Each binary pulsar tells part of the story, and together they reveal the full narrative of how dead stars can be recycled and how companions can be consumed by the objects they once nurtured. The gravitational interactions in binary pulsar systems also allow some of the most precise measurements in all of physics to be made using patient observation over decades of data collection. The orbital parameters can be determined with extraordinary accuracy, revealing subtle effects like the precession of the orbit's orientation, the Shapiro delay caused by light traveling through curved spacetime, and the orbital decay from gravitational wave emission. These effects depend on the masses and orbital geometry in specific ways that general relativity predicts exactly, allowing the observations to test the theory with precision unmatched by any other method available today. Binary pulsars thus serve as cosmic laboratories, where Einstein's theory faces its most stringent tests repeatedly and continues to pass with flying colors. The masses of neutron stars in binary systems have been measured with remarkable precision through these timing techniques, revealing that most neutron stars have masses close to 1.4 times the Sun's mass, but some reach 2 solar masses, or slightly more. The maximum mass a neutron star can have before collapsing into a black hole remains an active research question, with observations pushing the limit higher as heavier neutron stars continue to be discovered. The heaviest known neutron stars place constraints on the equation of state of matter at extreme densities, telling physicists how neutrons and possibly more exotic particles behave when squeezed together under immense gravitational pressure. Each new measurement refines our understanding of matter in conditions that cannot be recreated in any laboratory on Earth, ever. Binary pulsars continue to be discovered regularly as pulsar surveys become more sensitive and cover larger areas of the sky with greater completeness over time. Each new system adds to the population that astronomers can study, and occasionally, a discovery proves particularly valuable for testing physics or understanding evolution in new ways entirely. The field remains active decades after the first binary pulsar discovery, with new results continuing to emerge from both new discoveries and long-term monitoring of known systems across the world. The patience required to track these systems over years and decades rewards scientists with measurements impossible to obtain in any other way from any other type of astronomical source. These binary systems, with their intricate dances and dramatic fates, represent pulsars at their most dynamic. But all pulsars share a common destiny, regardless of whether they orbit companions or spin in solitary isolation. The rotation that makes pulsars visible is slowly draining away, energy lost to radiation that streams into space and can never be recovered by the spinning neutron star itself. Over immense spans of time, every pulsar will slow, its beam will fade, and the cosmic lighthouse will gradually go dark in the long quieting that awaits all of these remarkable objects, eventually. The slowing of pulsars happens continuously, invisibly, in increments so small that only the most precise measurements can detect the change over months and years of careful observation. Every rotation carries away a tiny fraction of the star's rotational energy, broadcast into space as electromagnetic radiation that streams outward at the speed of light and never returns to replenish what was lost. The magnetic field that creates the lighthouse beam also acts as a brake, dragging against the rotation and converting spin energy into the radiation that makes pulsars detectable in the first place. This process has been ongoing since each pulsar was born, and it will continue until the rotation becomes too slow to power detectable emission anymore. The rate of slowing varies enormously among different pulsars, depending on their magnetic field strength and rotation rate, and several other factors that influence energy loss mechanisms. Young pulsars with strong magnetic fields and rapid rotation lose energy quickly, their periods increasing by measurable amounts over just years or decades of observation since their recent birth. The Crab pulsar provides the clearest example, its period increasing by about 36 nanoseconds every day, a tiny amount that adds up to significant slowing over centuries and millennia. In 1,000 years, the Crab will rotate noticeably slower than it does tonight, its beam somewhat less powerful, its lighthouse somewhat dimmer than it appears to us now. Old pulsars, with weaker magnetic fields and slower rotation, lose energy much more gradually, their periods changing by only tiny fractions of nanoseconds per year in barely detectable decline. Millisecond pulsars are especially stable. Their weak fields and rapid rotation combining to produce energy loss rates so low that they will continue pulsing for billions of years into the future without significant change. Some millisecond pulsars will still be spinning and beaming when the sun exhausts its hydrogen fuel and swells into a red giant, outlasting our star and our entire solar system in their patient rotation. The stability that makes them excellent clocks also makes them nearly immortal on any timescale that matters for astronomy today. The energy lost by pulsars does not simply disappear, but flows outward into the surrounding space, sometimes creating beautiful structures visible to telescopes observing at various wavelengths across the electromagnetic spectrum. The Crab Nebula glows brightly because the Crab pulsar continuously pumps energy into the gas surrounding it, accelerating electrons to speeds where they emit visible light and X-rays detectable across the entire distance, separating us. This pulsar-wind nebula represents the visible evidence of energy loss, the spin of the neutron star being converted into the glow of the surrounding cloud in real time. Other pulsars create similar structures, their winds shaping and illuminating the material around them in patterns that reveal the geometry of the invisible magnetic fields. The period increase that represents slowing can be measured with extraordinary precision. For pulsars, that have been observed over long-time baselines spanning years or decades. Astronomers maintain timing models that predict exactly when each pulse should arrive at Earth, and deviations from these predictions reveal the gradual spin down occurring continuously beneath the apparent regularity. The precision of these measurements allows even tiny period changes to be detected, turning pulsars into laboratories for studying energy loss mechanisms and magnetic field evolution over observable timescales practically. What seems like a steady clock is actually running down, just so slowly that only careful measurement reveals the gradual decline happening perpetually. Some pulsars experience occasional glitches, sudden small increases in rotation rate that interrupt the steady slowing trend with unexpected jumps upward in spin frequency temporarily. These glitches likely result from internal processes, perhaps the superfluid interior transferring angular momentum to the crust, or the crust itself cracking under stress from the changing rotation rate. The Vela pulsar has experienced many recorded glitches since observations began, each one causing a tiny speed-up, followed by gradual recovery toward the normal slowing trend over weeks or months afterward. Glitches provide windows into the interior structure of neutron stars, revealing that the inside is not solid throughout, but contains exotic states of matter that behave differently from ordinary materials anywhere. The long-term fate of a pulsar depends on how its properties evolve as it ages and slows over millions and billions of years of continuous rotation and energy loss. The magnetic field may decay over time, weakening from the intense values present at birth to more modest strengths that reduce the breaking torque and allow slower energy loss. This field decay is not well understood theoretically, with different models predicting different timescales and patterns of decline depending on the physics assumed to operate inside the neutron star interior. Observations of pulsars at different ages help constrain these models, revealing that field decay does occur, but on timescales that remain somewhat uncertain precisely. Eventually, every pulsar will cross what astronomers call the death line, the boundary in the diagram of period versus period derivative, where the emission mechanism can no longer sustain itself against the slowing rotation. Below this line, the electric fields in the magnetosphere become too weak to accelerate particles to the energies needed to produce radio emission, and the beam fades below detectability permanently. The pulsar does not stop rotating when it crosses the death line, but simply stops producing the radiation that makes it visible to distant observers, like us, across the galaxy. The neutron star remains, spinning in the darkness, but the lighthouse has gone dark and the cosmic beacon no longer flashes its signal into space. The galaxy contains an estimated 100 billion neutron stars accumulated over its entire history of star formation and stellar death, continuing for over 13 billion years. Only about 200,000 of these are expected to be active pulsars, with beams currently crossing Earth's line of sight and potentially detectable by our instruments today. The vast majority are old, dead pulsars that crossed the death line long ago and now spin silently in the darkness between stars, invisible to radio telescopes and undetectable by any current method. These silent spinners vastly outnumber the active pulsars we can observe, a hidden population of ancient stellar remnants drifting through the galaxy without announcing their presence to anyone anymore. The dead pulsars do not decay or disappear, but persist essentially forever as neutron stars, their extreme density making them stable against further collapse or disruption under normal circumstances in typical galactic environments. They cool gradually over billions of years, their surfaces fading from the million-degree temperatures of youth to merely thousands of degrees in extreme old age. But they remain intact and spinning throughout. The rotation continues even without producing detectable emission. Angular momentum preserved, unless something acts to remove it through interaction with another object, gravitationally. In isolation, a dead pulsar would spin forever, gradually slowing, but never stopping. A silent remnant of the star that created it through violent collapse long ago. Some of these silent neutron stars occasionally become visible again through chance encounters or rare events that reveal their presence to observers across cosmic distances. A neutron star passing through a dense cloud of gas might accrete material that heats up and emits X-rays, briefly illuminating the otherwise invisible object for astronomers who happen to be watching that region of sky. Neutron star mergers, like the one detected in 2017, reveal pairs of these objects that may have been invisible before the final spiral brought them together, catastrophically. Most dead pulsars, however, will never be seen, spinning on through eternity in the silent darkness between the stars that light our galaxy at night. The pulsars we observe today represent a brief window into objects that will long outlast us and our civilization and our species, and perhaps even our sun itself in the cosmic future ahead. The fastest millisecond pulsars will still be spinning billions of years from now, when Earth is long gone and the sun has faded to a white dwarf cooling slowly in what was once our solar system. These ancient lighthouses, born from the deaths of stars before our planet even formed, will continue their patient rotation through eons we cannot imagine or predict today. The beam that sweeps past Earth tonight has been sweeping for millions of years and will continue sweeping for millions more, a signal from the deep past reaching into the distant future. The pulsar PSRJ 1748-2446 AD, spinning 716 times every second, will continue its rapid rotation for timescales that make human history seem instantaneous. It was recycled by a companion star long before the first humans looked up at the night sky, and it will still be spinning long after the last human thought has faded from the universe entirely. The equator of this city-sized object races at nearly a quarter of light speed tonight, as it has for millions of years, as it will for millions more. This is the timescale of pulsars, the deep time of the cosmos, where human concerns are brief sparks against the eternal darkness. The universe contains these objects, scattered throughout the galaxy, some beaming actively, others spinning silently, all remnants of stars that lived and died to create them through the ages. They keep time more accurately than any human clock. They test physics more precisely than any human laboratory. They reveal matter in states more extreme than any human experiment can create. They are lighthouses of the cosmos, beacons from dead stars, spinning signals from the ancient past, reaching forward into the unwritten future across the void between worlds. The galaxy pulses with their presence, most invisible to us. A few fortunate enough to have beams that sweep across our small blue planet occasionally. Tonight, somewhere in the sky above, radio waves from distant pulsars are arriving at Earth after journeys spanning thousands of years across the empty spaces between stars, silently. Some of these pulsars have been known for decades, their timing tracked by observatories around the world that add each new pulse to databases stretching back generations of astronomers. Others remain undiscovered, their beams either missing Earth entirely or awaiting the survey that will finally detect their regular signals for the first time ever. The search continues, patient and methodical, knowing that the pulsars are out there spinning whether we have found them yet or not, waiting to be revealed. The Crab pulsar flashes 30 times each second at the heart of its glowing nebula, energy from a collapse that happened when the Song dynasty ruled China, still powering its lighthouse beam tonight. Vela pulses 11 times per second from within its own supernova remnant, occasionally glitching as its interior adjusts to the stresses of slowing rotation over the millennia. The Hulse-Taylor binary pulsar continues its orbital dance, the two neutron stars drawing closer together by about a meter each year, destined to merge in roughly 300 million years from now, catastrophically. These individuals, and thousands like them, populate our galaxy with spinning remnants of dead stars that refuse to be silent in their afterlives entirely. The study of pulsars continues to reveal new surprises decades after the first discovery in that English field in 1967 by a graduate student examining paper charts carefully. New types of pulsars have been found, new behaviors have been observed, new uses for their precise timing have been developed by generations of astronomers, building on previous work continuously. The gravitational wave background has been detected using pulsar timing arrays, confirming that space-time itself ripples with the passage of waves from distant merging black holes across the observable universe. Pulsars have moved from mysterious signals to essential tools for probing physics at the most fundamental levels available to modern astronomy today. And so these cosmic lighthouses continue their vigil, spinning in the darkness, beaming across the light years, keeping time with a precision that shames any mechanism of human construction. They were born from violence but persist in patience, created in moments of collapse but enduring for eons of steady rotation through the quiet dark between stars. The fastest spin 700 times per second, while the slowest turn once every several seconds, but all share the common nature of compressed matter announcing its presence to the universe continuously. They are the dead stars that refuse to be silent, the collapsed cores that found new purpose in spinning, the beacons that light the galaxy for those who know how to see them properly. The night sky looks quiet from Earth, but the radio universe pulses with the steady rhythm of 1,000 known pulsars and countless more awaiting discovery in the years ahead. Each pulse is a message from a dead star, a reminder that the universe is far stranger and more wonderful than casual observation would suggest on any given evening. The light from ordinary stars speaks of fusion and heat, but the pulses from neutron stars speak of collapse and density, and the exotic physics of matter crushed beyond recognition entirely. Both contribute to the symphony of the cosmos, audible to those with the instruments and patience to listen carefully across the vast distances separating us from them. The pulsars will continue spinning long after these words are forgotten, long after the instruments that detect them have crumbled to dust on a planet that may no longer exist in recognizable form. They care nothing for human observation and would spin just as faithfully if no one ever detected their beams crossing the emptiness between their locations and ours endlessly. Their existence is independent of our awareness. Their physics operates whether we understand it or not. Their beams sweep the galaxy regardless of who or what might be watching from afar. We are fortunate to have found them, fortunate to understand them as well as we do, fortunate to have these cosmic lighthouses illuminating the physics of the extreme universe for our careful study and quiet wonder at their remarkable persistence through cosmic time everlasting. Good night from the drowsy astronaut, and I hope to see you again tomorrow.